In ancient times, humans gathered around campfires, peering into the darkness and wondering what lay beyond. Today, not much has changed, except our campfires are now massive telescopes like the James Webb, peering out to the edge of the observable universe. But no matter how far we look, there's always a point where the light stops reaching us. Beyond that, it's all guesswork. The observable universe is essentially a sphere centered on us. It's defined by how far light has traveled since the Big Bang, about 14 billion years ago. But because space has been expanding, the farthest things we can see are now around 45 billion light-years away. That's a lot of ground to cover, or space, technically, with roughly 200 billion galaxies full of stars packed inside. But this edge we talk about isn't like a wall you can touch. It's not a border where you'd bump into something. It's more like an edge in time. We're seeing ancient light, looking further and further back until eventually, there's nothing left to see. It's a hard cutoff because the universe wasn't always around. What's frustrating is that we know there's more beyond that line, probably a lot more, but we'll never get to see it. Light simply hasn't had enough time to travel that far. It's a cosmic speed limit that not even the universe itself can break. And since nothing can move faster than light, anything beyond that horizon is effectively out of reach forever. But here's the thing. Even though we can't see it, the universe doesn't just stop there. Whether it's finite or infinite, it stretches far beyond what our eyes, or even our best instruments, can detect. It's like staring at the ocean. You know it keeps going over the horizon, but you can't prove it just by looking. We're left with theories, educated guesses, and a whole lot of curiosity about what's hiding in the darkness. When we talk about the edge of the universe, it's easy to picture some kind of cosmic wall where space just ends. But that's not how the universe works. What we think of as an edge is more of an optical illusion created by time and light. We're not seeing the universe as it is right now. We're seeing it as it was. Every distant galaxy is like a time machine showing us the past. Because of cosmic expansion, the light from faraway objects takes billions of years to reach us. By the time it arrives, the objects themselves are much farther away. This means the edge is really a limit on how far back in time we can look. Beyond that point, light hasn't had enough time to reach us. But what if you could magically teleport to that edge? What would you see? Not a wall. You just keep going. Scientists have tried to understand whether the universe is finite or infinite. One idea is that the universe could be shaped like a hypersphere, a 4D version of a sphere where space curves back on itself. In a hyperspherical universe, you could fly in one direction forever and eventually end up back where you started. It sounds bizarre, but this model would neatly explain why space appears flat to us. The Planck satellite measured the curvature of the universe with extraordinary precision in 2013, showing it's either perfectly flat or so slightly curved that the radius of curvature could be over 1 trillion light-years. In other words, if the universe does curve, it's so huge that it feels flat to us, just like how the Earth looks flat when you stand outside. Another wild idea? The universe could be shaped like a hypertenet, technically a 3 torus. In this model, space loops back on itself in multiple directions, creating a kind of cosmic hall of mirrors. Light could wrap around, making it possible to see the same galaxy from different angles or even at different points in time. Imagine watching a star explode in one part of the sky, then turning around and seeing the same explosion billions of years earlier. It's trippy, but scientists like Jean-Pierre Luminet have seriously considered this possibility. So far, no repeated patterns have been found, but the search continues. If the universe is infinite, though, it never ends. It keeps going forever, with no walls or looping back. That raises another mind-bending idea. In an infinite universe, every possible combination of particles could happen, not just once, but infinitely many times. That means somewhere out there, incredibly far away, there could be another version of you watching this same video or reading this same article right now. Sounds ridiculous, right? But mathematically, it's possible. Whether the universe is finite or infinite, what we call an edge is more about how far we can look. Beyond that, the universe just keeps going, even if we'll never be able to see it. It's like being in a vast forest at night with a flashlight. The trees don't stop where the light fades. They just keep going unseen. What could be lurking beyond the observable universe? It's one of the biggest cosmic mysteries out there, and scientists have plenty of theories, some grounded in physics, others that sound like pure science fiction. But here's the catch. Even the most outlandish ideas are backed by serious math. One of the most debated theories is the multiverse hypothesis, which suggests our universe is just one bubble in a vast cosmic foam. This idea comes from eternal inflation, proposed by Alan Guth in the 1980s. During the rapid expansion right after the Big Bang, space might have inflated unevenly, splitting into countless bubble universes. Each bubble could have different physical laws. In one, gravity might be weaker. In another, stars might never form. And yes, there could be one where pineapples rule the planet. Physicists like Andre Linde have spent decades refining this model, showing that if inflation happened once, it could happen endlessly. Another theory is the brain-world model, rooted in string theory, which suggests our universe is a 3D brain floating in higher dimensional space. Imagine a sheet of paper drifting in a larger room. We're on the paper, unaware of what's happening in the rest of the room. In this model, gravity could leak into other dimensions, which might explain why it feels so weak compared to other forces. Physicists like Lisa Randall and Raman Sundram proposed this idea in 1999, and it could mean there are other brains, other universes, floating nearby, possibly just millimeters away. Then there's the concept of quantum fluctuations, where space itself is never truly empty. Even in a vacuum, particles pop in and out of existence. Some physicists believe entire universes could emerge from these fluctuations. Alexander Vilenkin argued that if space is infinite, this process could happen infinitely. In theory, universes could be constantly forming beyond our observable horizon, popping into existence like cosmic bubbles. Finally, some theories challenge the idea of a single beginning. The cyclic model, proposed by Paul Steinhardt and Neil Turok, suggests the universe goes through infinite cycles of expansion and contraction. Instead of a one-time Big Bang, there could be endless big bounces. If true, the universe beyond our observable edge might just be another version of, well, this. All these theories are bold, some controversial, but none are purely imaginary. They're grounded in math, physics, and our best attempts to explain what we can't see. And who knows, maybe one day we'll find evidence that our cosmic bubble is just one of many, or that reality itself is far stranger than we ever imagined. Dark flow is one of the strangest mysteries in cosmology, the kind that makes scientists scratch their heads and wonder if there's something huge lurking beyond the observable universe. It all started in 2008 when Alexander Kashlinsky and his team at NASA's Goddard Space Flight Center analyzed data from the Wilkinson Microwave Anisotropy Probe (WMAP). They noticed something weird. Hundreds of galaxy clusters were drifting toward a specific region near the constellations Centaurus and Hydra at speeds of 600 to 1,000 kilometers per second. That's fast, really fast. The problem? There's nothing visible pulling them. Gravity is the only force that could cause such large-scale motion. But according to our models, there simply isn't enough mass within the observable universe to explain it. This unexplained movement was dubbed dark flow, and it sparked controversy almost immediately. How do we know these galaxies are moving like this? It comes down to something called the kinematic Sunyaev-Zeldovich effect. When cosmic microwave background, CMB, radiation, the leftover light from the Big Bang, passes through galaxy clusters, it picks up tiny boosts of energy. By measuring these slight changes, scientists can determine how fast the clusters are moving. Kashlinsky's team found a consistent drift across billions of light years, something that shouldn't be happening if the universe is isotropic, meaning the same in all directions. So what could be causing it? One theory suggests a massive structure beyond our observable horizon, something like a colossal supercluster or even a region of higher density matter left over from the early universe. It could be remnants of quantum fluctuations from before cosmic inflation, tugging on our local patch of the universe. Another possibility is a multiverse interaction, another universe exerting gravitational influence on ours. Sound wild? Sure, but that's how far scientists are willing to go to explain this. Of course, not everyone is convinced. In 2013, data from the Planck satellite, a more advanced probe than WMAP, failed to find clear evidence of dark flow. Critics argued that Kashlinski's findings might be statistical noise or errors in the data, but Kashlinski's team fired back, claiming they could still detect signs of the flow even in Planck's data. The debate is ongoing. Whether dark flow turns out to be a statistical fluke or proof of something massive beyond the edge of the observable universe, it forces us to confront how little we truly know. It's a reminder that the universe might be hiding secrets far bigger than we ever imagined. And maybe, just maybe, we're only seeing the tip of the cosmic iceberg. The horizon problem is one of the biggest puzzles in cosmology. It comes down to this. Why does the universe look so uniform in every direction when there hasn't been enough time for light, or any information, to travel across it? According to the standard Big Bang theory, regions of the universe separated by billions of light years have never had any contact with each other. Yet, when we look at the cosmic microwave background, CMB, the leftover radiation from the Big Bang, it is almost the same temperature everywhere, about 2.725 Kelvin. That shouldn't be possible. Enter cosmic inflation, a theory proposed by Alan Guth in 1981. Inflation suggests that in the first 10 to the minus 33 seconds after the Big Bang, the universe expanded faster than the speed of light, blowing up by a factor of 10 to the 26. That's like going from the size of a proton to the size of a galaxy in less than a trillionth of a second. This sudden expansion would explain how distant regions had time to mix before they were pulled apart. Essentially, everything started out in thermal equilibrium before inflation stretched space so rapidly that these regions became separated. But what caused inflation? Physicists point to a hypothetical field called the inflaton field, with a quantum state known as a false vacuum, a high-energy state that suddenly decayed, releasing enormous energy and driving the rapid expansion. After this brief but violent period, inflation ended, and the universe continued to expand at a slower pace, eventually cooling down to form matter as we know it. The beauty of inflation is that it solves multiple problems at once. Besides the horizon problem, it also explains the flatness problem, why the universe appears geometrically flat, and the monopole problem, the absence of magnetic monopoles that should theoretically exist in large numbers. Measurements from the Planck satellite in 2013 further supported inflation by showing tiny fluctuations in the CMB consistent with quantum variations stretched during inflation. Yet, cosmic inflation isn't a closed case. Competing models, like ekpyrotic theory, suggest that our universe was born from the collision of two higher-dimensional branes, skipping the need for inflation entirely. Meanwhile, some physicists, including Roger Penrose, argue for a cyclic model where the universe expands and contracts over infinite cycles. Regardless of which model turns out to be right, inflation remains one of the most elegant solutions we have. It turns the chaotic early universe into something orderly, or at least orderly enough to produce galaxies, stars, and ultimately us. But the fact that we're still debating the details shows how much of the universe remains a mystery. And honestly, isn't that what makes it so fascinating? Could we ever know what lies beyond the observable universe? It's one of the most profound questions in cosmology, and the short answer is probably not. But that doesn't mean scientists are giving up. The fundamental limit is the speed of light. Nothing can travel faster. As space keeps expanding faster than light can cross it, the distant regions of the universe slip further away. Eventually, even galaxies we can currently see will drift beyond our reach. In about 100 billion years, observers in our galaxy won't be able to see any other galaxies at all. The cosmic horizon is always moving, and we're stuck inside it. But are there loopholes? Some theories suggest there might be ways to peek beyond this limit. Gravitational waves, ripples in space-time first detected by LIGO in 2015, could carry information from regions we can't see. If something massive lurks beyond our horizon, like a giant supercluster or a cosmic void, its gravitational imprint could still reach us. It's like hearing a loud noise from behind a wall. You don't see what's making the sound, but you know something's there. Quantum physics also offers some wild possibilities. The concept of quantum entanglement, where particles remain connected regardless of distance, might allow information to bypass the speed of light, though this remains speculative. Another idea is that the universe could be embedded in higher dimensions, like in brain theory, where gravity could leak between universes. If true, detecting these leaks could offer clues about what lies beyond our own cosmic bubble. One of the most ambitious concepts comes from Hawking radiation, proposed by Stephen Hawking in 1974. While typically associated with black holes, some scientists wonder if similar radiation could be emitted from the edge of the observable universe, carrying information about what's outside. So far, there's no evidence of this, but it's a tantalizing thought. Ultimately, the biggest hurdle is time. As the universe expands and ages, the regions we can observe will shrink. We're living in a brief cosmic window where the universe is still young enough to study. In the far future, the sky may go dark, and the cosmic microwave background will fade. If we want answers, the time to search is now. Maybe we'll never know for sure what's out there. But science has a habit of surprising us. From discovering exoplanets to detecting gravitational waves, we've shattered impossible limits before. Who's to say we won't do it again? The universe is full of mysteries, and it seems like it wants us to keep asking questions. Human curiosity has always been a force stronger than gravity. From the moment our ancestors first looked up at the stars, we've been obsessed with figuring out what's out there. Fast forward to today, and we're still staring into the cosmic void with telescopes like Hubble and James Webb, pushing the limits of what we can see, and more importantly, what we can imagine. Why do we care so much? Part of it comes down to survival. Understanding the universe helps us grasp our place in it. The more we know, the better our chances of navigating the future. But it's more than that. We build billion-dollar observatories not because we need to, but because we want to. We want to know if there are other Earths orbiting distant stars, if life exists beyond our planet, or if there's something massive lurking beyond the observable universe pulling galaxies with a mysterious force. Some of the most important scientific breakthroughs, like Einstein's theory of relativity or the discovery of exoplanets, started with curiosity-driven questions that seemed impossible to answer. And when we do find answers, it only opens more questions. What caused the Big Bang? Are we living in a multiverse? Is there another version of you reading this article right now? The universe never runs out of mysteries. The truth is, we may never see beyond the cosmic horizon. But the edge of the observable universe isn't just a limit, it's an invitation. As long as there are questions left to ask, humanity will keep searching. Because the moment we stop wondering what's out there, that's when we stop moving forward. And something tells me we're not the kind of species to stop.